Welcome to the virtual tour in the laboratory of Attosecond Physics of the Max Planck Institute of Quantum Optics in Garching. Our lab is a part of the research training network MEDEA. Enjoy your virtual visit.
This is AS1 Beamline of Laboratory of Attosecond Physics of Max Planck Institute of Quantum Optics. In the Attoelectronics group, we focus efforts in studying electronic response in the condensed phase. A key tool of our research, the light field synthesizer, a device that can synthesize light waveforms that spectrally span from deep infrared to the ultraviolet part of the spectrum. With this tool, we can tame the waveform of light down with a precision higher than half field cycle. Combining these fields with the soft X-ray attosecond pulses, we are now able to study the electron dynamics in solids. Example of our research includes the use of these pulses to control electrons inside the solid so as to emit EUV radiation. Study of the spectra and dynamics of EUV pulses from solids allows us to gain insight into the basic electronic mechanism as well as electronic structure in the solids with unprecedented resolution.
We're here at the AS5, where we do attosecond streaking experiments on ultra-fast photo emission. What is different to other beamlines at this institute is that we use metallic nanostructures. Nanostructures are interesting because light can fully penetrate them and thereby excite collective electron dynamics of all the electrons in the metal. This is useful because it enhances the electric field of the incoming light and also allows to confine the optical energy of the light to length scales on the order of the scale of the nanostructure, which is much smaller than the wavelengths of the optical light. We aim at a fundamental understanding of this plasmon dynamics and also exploring its potential as a link between conventional electronics and light wave electronics, a new kind and much faster electronics which is controlled by light.
In our beamline, we perform attosecond pump probe experiments. Optical fields with a pulse duration of a few femtoseconds are employed to trigger electron dynamics in a medium. As the temporal and spatial structure of the driving light field is entirely characterized, the material is excited in a controllable way. Radiation in the extreme ultraviolet range with a duration of a few hundred attoseconds is used to probe the induced dynamics. As the motion of the electrons evolves on these short timescales, the attosecond pump probe technique provides real-time resolution. The attosecond pulses are generated by focusing the few femtosecond pulse into a dilute gas jet of noble gas atoms. Photoelectrons are freed in the process of tunnel ionization and subsequently accelerated in the driving laser field. In the recombination process, a train of attosecond pulses in the extreme ultraviolet spectral range is emitted. For cosine few-cycle driving pulses, the highest energy photons originate from one attosecond pulse, which can be isolated by spectral filtering. After the generation of the attosecond pulse, it is spatially separated from the fundamental field. The optical and XUV radiation propagate in the two arms of a Michelson interferometer. Here, the temporal delay between the pump and the post-pulse can be varied. In the experiment, the presence of the femtosecond field influences an experimental observable related to the attosecond pulse. For example, the energy distribution of photoelectrons emitted by the XUV radiation or the spectrum of the attosecond pulse transmitted through the sample. With these techniques, it is possible to gain real-time access to the excited electron dynamics in gases, for example ozone, and different solids like dielectrics or semiconductors.
Behind me, you can see the AS3 beamline in the Max Planck Institute of Quantum Optics. Our main research goal is to observe electron motion in solids and molecules on the attosecond timescale. The tools we're using is time-resolved photo emission and attosecond streaking. Along the beamline, we generate attosecond pulses containing photon energies of up to 150 electron volts via high harmonic generation. Employing dielectric and metal filters, we isolate single attosecond pulses using the intensity gate technique. Because the electron inelastic mean free path in our energy region is only a few angstrom, we can only examine atomically clean samples. Therefore, all of them have to be prepared in situ. The main chamber is therefore split into two parts. Isolated from the experiment volume, a preparation part allows to produce a variety of samples, from simple metal surfaces to complex systems such as thin molecule layers or high temperature superconductors. After preparation, we can then transfer a sample into the unspoiled experiment part. There, we use a collinear near-infrared and XUV interferometer and a time-of-flight and hemispherical electron analyzer to trigger and follow some of the most fundamental processes in nature with attosecond precision.